The first thing I have to tell you is that you probably already have some picture in your head of what antimatter is, and it's probably not quite right. Most people think antimatter is just regular matter with something flipped, like a mirror image. That idea is partly true, but it misses the most interesting part. The story of antimatter is one of the most beautiful stories in all of physics, because antimatter was not discovered by someone walking into a laboratory and finding something strange. No, antimatter was discovered by a man sitting at his desk, staring at equations, and finding something that should not have been there. Here's what happened. There was a physicist named Paul Dirac, a very brilliant fellow. In the late 1920s, physicists already knew about quantum mechanics, and they also knew about relativity. Dirac wanted to combine the two. He wanted a single equation that respected both theories. So he worked and worked until he found the simplest possible equation, beautiful, elegant, and extremely successful at describing how electrons behave. But there was a problem. The equation had solutions that made no sense at first. Some solutions had negative energy. What does that even mean? An electron with negative energy? It sounded like nonsense. Most people would have thrown those solutions away and said, the math is giving us garbage, let's ignore it. But Dirac didn't do that. He took the strange answer seriously. He asked, what if these solutions are trying to tell us something? What if nature actually uses them? From this idea, Dirac made a bold prediction. He said there must exist a particle no one had ever seen before, a particle exactly like the electron, with the same mass and properties, but with the opposite electric charge. Since the electron is negative, this new particle would be positive. He called it the anti-electron. Today, we call it the positron. And a few years later, it was found. A physicist named Carl Anderson was studying cosmic rays, particles raining down from outer space. In his experiments, he discovered a particle that curved the wrong way in a magnetic field. It had the mass of an electron, but behaved as if it had a positive charge. The positron was real. Dirac had predicted it using pure mathematics, and nature agreed. This discovery raised an even bigger question. If the electron has an antiparticle, what about the other particles? What about the proton? What about the neutron? People understand that the antiproton has the opposite charge of the proton, but then they ask about the neutron and say, wait, the neutron has no charge. How can it have an antiparticle? What's the opposite of nothing? Here's the key idea. An antiparticle is not defined only by opposite electric charge. Particles have many properties besides charge. When you flip all of those properties, you get the antiparticle. So yes, there is an anti-neutron. The difference is easy to see experimentally. Put two neutrons together and nothing special happens. But put a neutron and an anti-neutron together and they annihilate. Their entire mass is converted into energy, producing gamma rays and other particles. When matter meets antimatter, they don't just mix like chemicals, they annihilate completely. 100% of their mass turns directly into energy. Think about burning wood. Only a tiny fraction of the mass becomes energy. Even in nuclear reactions, only about 1% of the mass turns into energy. But with matter and antimatter, everything is converted into pure light. This isn't just theory, it happens in laboratories. We can make positrons, observe them, watch them curve the wrong way in magnetic fields, and then watch them collide with electrons. When they meet, both particles vanish and two gamma rays fly out, carrying all the energy that used to be their mass. Now here's where things get even deeper. To understand what a positron really is, we look at the mathematics. Physicists draw diagrams where space goes one direction and time goes another, usually upward. A line represents a particle moving through space and time. When we calculate the probability for an electron to move from one point to another, the math works fine when time moves forward. But surprisingly, the equations also allow an electron to move backward in time. That sounds disturbing, but it's real. When you examine this backward-moving solution, you find something remarkable. It has the same mass and interactions as an electron, but it behaves as if it has a positive charge. It curves the wrong way in a magnetic field. That backward-in-time electron is the positron. So from this viewpoint, a positron is not a separate particle. It is an electron moving backward in time. Imagine an electron moving forward in time. It interacts with light, then briefly moves backward in time, then turns around and moves forward again. To us, watching time flow normally, it looks like this. Light creates an electron-positron pair. They exist for a while, then annihilate and turn back into light. But mathematically, it's just one continuous line. This is not philosophy. This is how the calculations actually work, and the experiments confirm it. For every particle in nature, there is an antiparticle. Protons have antiprotons, neutrons have antineutrons. When matter and antimatter meet, they annihilate. On Earth, positrons don't last long because electrons are everywhere, in walls, in atoms, in air. But if you're clever, you can trap positrons using magnetic fields and keep them circulating for days without touching anything. In fact, we accelerate electrons and positrons in opposite directions and smash them together at high energies. When they collide, they produce new particles, sometimes particles we've never seen before. This is one of the main ways we explore the fundamental structure of nature. Now imagine taking this further. If anti-electrons, antiprotons, and antineutrons exist, then anti-atoms could exist too. Antihydrogen would consist of an antiproton with a positron orbiting it. It would behave exactly like hydrogen and emit the same light. You couldn't tell the difference just by looking. An entire antimatter world would work just like ours. Anti-chemistry, anti-biology, everything the same. Anti-people would live normal lives and never know they were made of antimatter, unless they touched ordinary matter. Then, annihilation. This leads to one of the biggest mysteries in physics. If matter and antimatter are so symmetrical, the universe should have begun with equal amounts of both. But when we look around, everything we see, Earth, stars, galaxies, is made of matter. Where is the antimatter? If large antimatter regions existed, we would see massive annihilation at the boundaries, producing gamma rays. But we don't see that. The universe appears to be almost entirely matter. Why? There must be a tiny asymmetry in the laws of physics, something that created slightly more matter than antimatter in the beginning. Almost everything annihilated, but a small excess of matter survived. That tiny leftover is us. Every star, every planet, every person, we are the residue of the great annihilation at the birth of the universe. What caused that asymmetry? No one knows. It's one of the great unsolved problems in physics. That's how science works. You discover something beautiful, matter, antimatter, positrons, matter-energy conversion, and then you uncover an even deeper mystery. We keep experimenting. We keep looking at the sky. We keep writing equations, and maybe someday someone will figure it out. And here we are, made of matter that barely survived, trying to understand how it all works.